Your assignment this week involves developing a spreadsheet to calculate Marin factors. I show a spreadsheet here that I have developed, and what we are trying to do is calculate all of the Marin factors, Ka, Kb, Kc, Kd, and Ke. So our hope is that we can take these equations over here, equations 619, 620, 626, and then tables associated with temperature and reliability, as well as rotating and non-rotating circular specimens. We're going to stick with circular specimens right now because it's going to get way too complicated to include everything. So what you have to do is set your system up so that you can very easily, as we see over here on the left side, determine what units you're working in. You'll notice that I have in row 2, I have the units listed, and in column B, I have a drop-down menu that allows me to choose English or metric units. And when I choose those units, if I'm in the metric system, I use shaft diameters measured in millimeters and stress in megapascals. If I switch to English units, I'm measuring shaft diameters in inches and stress in kpsi. How do I do that? When I want to create a drop-down menu, I go to the Data tab at the top, and I go to Data Validation. So let me just make one up right here. Let's do a drop-down menu in here, and I'm going to go and create a tab. You'll notice I have a number of tabs down here. At the bottom of my screen that list Marin factors. This is this particular sheet in the worksheet. Equivalent areas. In the Equivalent Areas tab, I have those areas from table 6.3 and Shigley, but for now I'm only doing circular shafts. So if I go from a rotating to a non-rotating circular shaft, I have to change the effective diameter of that shaft. I have to convert it to 37% of the actual diameter. If I go to the Fatigue Fraction tab, I have to recreate this F curve. Now you aren't going to need that to calculate Marin factors. You're going to need that a little bit later. So let's not worry about it for now, but there is a way for you to calculate this curve, F factor, as a function of the ultimate tensile strength in both English and metric units. We are going to need the reliability data, which comes out of table 6.5. So we're going to take that data, and I converted it into tabular form over here on my worksheet so I can reference it. I have to take the temperature data, which was out of table 6.4. I again created a spreadsheet so that I could plot the temperature correction factor, Kd, which appears in degrees C in column B and in degrees F in column E. And I made those plots for Kd as a function of degrees Fahrenheit and Kd as a function of degrees C. And then I fit a fourth order polynomial to them, and I get this equation right here, which I can then use in calculating my temperature correction factor when I go back to the Marin factors worksheet. But I was on to something a moment ago, and that is there are drop-down lists that I have to create. And in these drop-down lists, I create a column somewhere on one of my worksheets that allows me some choices. And I list all the choices that I need. Under the units column, I just want to go English and metric. For the surface correction factor, I want to include ground, machined, cold drawn, hot rolled, as forged, and I like to include an option that we can simply ignore that correction factor. Under the loading condition, I have rotating, non-rotating, or just ignore it. Under the loading factor, I have bending, axial, torsion, or ignore. And under the temperature correction factor, I have Celsius, Fahrenheit, and ignore. So I want to have all of those in drop-down windows. So let me go back to this Marin factors worksheet. And I'm going to create an artificial drop-down window in here. So I'm going to use the data validation tab to do that. But first I'm going to go and create a drop-down list. And I'll just create something here that I'll call yes and no. Okay, so now I'm going to go back to the Marin factors worksheet. I'm going to click on this cell that I want to create a drop-down menu in. I go under the Data tab at the top of the worksheet. I go under the Data tab at the top of the worksheet. I click on Data Validation. I activate the Data Validation menu item, and I say let's choose from a list. And in the source, I'm going to click. And now I'm going to go to my drop-down list and do this. And after I do that, I'm going to hit Enter, OK, And when I go back to the Marin factor worksheet, you'll see, sure enough, I have a drop-down menu. So that means I can choose yes or no. Now, I did this because I wanted to show you how to create drop-down menus. I said that right off the bat, I can choose English or metric units through a drop-down window. You'll notice that I have to enter my ultimate tensile strength, and it tells me what the units should be for that entry based upon what I chose in column B, row 2. For the surface condition correction factor, I have a number of choices: ground, machine, cold drawn, hot rolled, as forged, and ignore. If I hit ignore, you'll notice that my Ka value is set equal to 1. Under the geometric size correction factor, I have the option of rotating or non-rotating or ignore, so I could just ignore that. And if I do it, it puts my correction factor at 1. I have a loading factor for bending. That's load factor is Kc. If I'm under bending, then it's automatically set to 1. And under temperature correction factor, I could ignore that as well, which sets that correction factor equal to 1. And under reliability, if I'm at 50% reliability, it sets that correction factor equal to 1. Now that we've shown how to create drop-down menus, we have to use those drop-down menus. And let me just imagine that I'm going to be operating in the English system. I have a shaft diameter of, make it whatever you want. Let's just go ahead and make it 8 inches. Let's imagine my ultimate tensile strength is 180 kpsi. These are things that I do have to enter into it. So what we're going to do is look at the surface condition correction factor, and I have a bunch of drop-downs: ground, machine, cold drawn, hot rolled, as forged, and ignore. And those set conditions for calculating the A and B factors that show up in the equation that is used to calculate the surface condition correction factor. So what we need to know is the A factor out in front depends upon whether or not we have selected the ground condition, the machined condition, cold drawn, hot rolled. This is complicated, and so you need to set up a bunch of nested if equations in order to do it. And we also need to know whether we're in the English or the metric system. So I have in here a condition: if we have chosen that the surface has been ground, and if we are in the English measurement units, then we use the A factor of 1.34. If we're not in the English units, we're going to use an A factor of 1.58 for the ground condition. So there's a lot of nested ifs that you have to generate. The exponent B, to which we raise the ultimate tensile strength, only depends on whether you're ground, machined, cold drawn, or hot rolled. It does not depend upon the units. So you'll notice that that prefactor A adjusts for the units, and so it varies. So if we do that, we can compare it to, say, a problem from the book. Example 6.3 asks us to do something in metric units. So I'm going to change this to metric. I'm going to choose my ultimate tensile strength. It says the ultimate tensile strength is 520 MPa. We're looking at a machined surface. So I'm going to use the machined drop-down, and I get a geometric surface correction factor of 0.86, which agrees with the example in the book. That's example 6.3. So what we just discussed is how these drop-down menus set a word that you compare to a set of parameters that are available through the equations that we have sorted out previously. So now if we go to the geometric size correction factor, let's imagine that we're in metric units. We'll extend the last problem where we have an 8 millimeter diameter shaft. It is going to be under conditions of rotating bending. And so you'll see that the equivalent diameter is the same as the diameter under conditions of rotating bending. We don't have to adjust it. And so our A factor remains the same, 0.860, but our geometric size correction factor here has a rather large if-then comparison. So what we're trying to do is sort out if we said to ignore. So if B9, that is the entry in the drop-down menu where I have chosen rotating, if I had chosen ignore, it sets the KB factor to 1. Otherwise, it looks to see if I chose axial loading. If I had chosen a different loading condition, so instead of bending, if I choose axial, the KB value has to be 1. So you need another condition in there. We're going to look at this KB again. If I chose an axial, I have to set KB equal to 1. But if I didn't ignore it and I didn't choose axial down here under the loading factor, then I compare my shaft diameter to the diameters that are listed in equation 620. And I've decided that if my shaft diameter is below 2.79 millimeters, then I need no correction factor. If it's, however, within this range, I need one correction equation. And if it's in a different range, I need another correction equation. And so those are all set up here in this conditional statement where I am comparing things that I've checked in column B to these various if statements up in here. Totally up to you how you sort that out. I understand that it might be a pain. If I go to non-rotating, then what I have to do is I need to convert the true diameter of the shaft to an equivalent diameter. I'm now at 37% of what I was at before. And that equivalent diameter is going to give me a different geometric modification factor. So in fact, it's greater than 1 in this case. But if I go back to rotating, I have a knockdown factor. If I have a temperature correction, then I would say, well, let's be in degrees Celsius. Suppose I have 450 degrees Celsius. Then my KD value here is 0.859. How am I going to get that KD value? Well, we come up here and decide whether or not I asked you to ignore it. If I had chosen ignore, it's just going to set that factor equal to 1. Otherwise, if I'm choosing the Celsius condition, I have this really ugly equation in here with powers of the temperature that I have chosen. I get those equations from my temperature correction curve fits. So I simply take these equations for degrees Fahrenheit and degrees Celsius. I used a conditional statement so that I decide if I'm using Celsius, then I have to use this equation. If I'm not using Celsius, then I have to use the other equation here. So those are the things that you have to do. Under reliability, I have something else that I have to do. If I'm above 50% reliability, let's say I want 99% reliability, well, my reliability factor knocks down the endurance strength. And how do I get that? Well, if I look at the equation for that, you're going to notice I have this index match function. So the index is helping me locate which row matches the chosen reliability. So if I go to the reliability data, I took table 6.5, I converted it into entries in an Excel spreadsheet. I used the match function to match the reliability that I chose in the drop-down menu. It determines which row I need to look at. And the index function takes that row and chooses the entry in column B at that row. So it's index match function. You might want to look at that. It's right here. In all cases, Excel provides really good help feedback so you can figure out how to implement those index and match capability functions. Now, the thing that I've left out is the SE prime, you will note, is 1/2 of the ultimate if in megapascals we are less than or equal to 1400. In English units, if we're less than or equal to 200 kpsi. Otherwise, we set it equal to 100 if we're greater than 200 or equal to 700 if we're greater than 1400. And to show you that that will work for this endurance limit calculation, let me go ahead and put something in here. Let's just put 1400. And it tells me my endurance limit is 700. That's good. What if I put 1500? It maxes it out at 700. If I change my units and I go to KPSI, clearly at 1500, it's going to choose the 100 as the endurance limit. Now, what I do is I estimate that endurance limit, I multiply by each of the Marin correction factors, and it gives me a fully corrected endurance limit, which I have right over here. And then in the next step, after our next lecture, we're going to learn something about mean stresses, adjusting for mean stresses, and how to estimate the high cycle fatigue lifetime using a calculation to find the F factor, which determines the fatigue strength at 1,000 cycles. And then we find the Baskin's law fitting parameters from that. And we move forward and can predict the number of cycles to failure for any given stress amplitude.